Today we're going to investigate one of our families of functions that we learned about from our library of functions. Today we're going to learn about quadratic functions. The standard form of a quadratic function, f of x equals ax squared plus bx plus c. We are all very familiar with, we factored polynomials that look like this, solved quadratic equations that look like this. And we're also familiar with what the graph of a quadratic function looks like. It looks like a parabola. Now, some special characteristics of a parabola. The first is that there's this vertical line that goes through the middle that acts as an axis of symmetry. So everything on the left-hand side of our axis of symmetry is mirrored to give us the right side of our parabola. Now there's also a very special point on every parabola, and that's either at the very bottom, or if we envision the parabola opening the other direction at the very top. This is called our vertex. Now our vertex is so important because, as I mentioned, it's either the very bottom of the graph or at the very top of the graph. If the lead coefficient a of a quadratic function is greater than 0, that tells me that my parabola will open up. In other words, it's going to look like this. And if my parabola opens up, what does that tell me about the vertex? It tells me that the vertex is a minimum. Now, if my lead coefficient is negative, then my parabola will open down. And it'll have a shape like that. When my parabola opens down, if you notice, the vertex is now at the very top, which indicates that your vertex is the maximum. Since the vertex is either the minimum or the maximum, it's going to help identify the range of the polynomial as well. When we're graphing a quadratic function that's in standard form, we first want to determine the orientation of our parabola. So is it going to open up or is it going to open down, which we decide by that lead coefficient a. Once we know the orientation, then we're going to find and plot the vertex. When we have a quadratic in standard form, the vertex can be found using this formula. This is the x-coordinate of our vertex, negative b divided by 2a, where a and b are those coefficients from the quadratic. And if you know the x-coordinate of an ordered pair, to find the y-coordinate, you just plug that in. And that's what this is saying. Again, this notation is indicating the y value when your x is equal to negative b over 2a. Once we've plotted the vertex, we're also going to plot 2 points on the left and the right-hand side of that vertex. Sometimes we'll use the x-intercepts, but they're not necessary. Just make sure that you're plotting 2 points on both the left and the right. So we have a quadratic function, f of x equals x squared plus 2x minus 8. Because my lead coefficient is positive, I know this graph is going to open up. And now I want to find the vertex. To find the vertex, again, the formula is negative b over 2a for the x value. And then I'll take that x value and plug it in to find y. So using my coefficients, here's my a, which is an invisible 1, right? And here's my b. So negative b is going to be negative 2 divided by 2 times a is 1. When I simplify this, negative 2 divided by positive 2 is negative 1. And to find the y value, I'm going to take that value of negative 1 and plug it into my function. So we have negative 1 squared plus 2 times negative 1 minus 8. This is 1 minus 2 minus 8, or negative 9. So my vertex is at negative 1, negative 9, all the way down here. And I know that my graph is going to open up like this, if you can see my cursor. Now, I'm going to go ahead and emphasize this axis of symmetry again. That axis of symmetry goes through your vertex, and it's going to act as a mirror. So our next step is to find points on the left and the right. So I'm just going to make a table of values to keep track of this. If this is my vertex, what is one x value that we could plot either on the left or the right? Since this is at negative 1, I can easily plug in x equals 0, and that'll give me 1 point to the right. When I plug in x equals 0, we can see that we get 0 plus 0 minus 8 is negative 8. So I have this point right here at 0, negative 8. This axis of symmetry is going to help us find a point on the other side, because this is just going to reflect over the axis of symmetry, and that's going to give me my third point. Now I need to plug in another x value. So staying with positive numbers, I'm next going to plug in x equals 1. When I plug in x equals 1, I get 1 plus 2 is 3, minus 8 is negative 5. So I have a point at 1, negative 5. And again, reflecting this point about the axis of symmetry, I get my fifth and final point. And then I can connect those to graph my parabola. So we see now that although I need 2 points on the left and the right for a total of 4 additional points, I only need to find 2 as long as I'm comfortable using the axis of symmetry and reflecting those points about that. F of x equals negative x squared minus 2x. First thing I notice is that I've got a negative lead coefficient, so I know this is going to open down. And one thing you might want to add here, when we're missing a term, if you look, it doesn't look like our quadratic trinomial we're used to, but I'm missing that c value. You can add the 0 there if it helps you identify the full standard form. It's not necessary though. So now I go to find my vertex. Again, the formula for the x coordinate is negative b over 2a, and then we're going to plug that in to find our y values. I find that the more often I actually write this formula out, the negative b over 2a, the easier it is for me to remember that formula. So negative b is negative 2. So the negative of negative 2 would be positive 2. Over 2 times a is negative 1. 2 divided by negative 2 is negative 1. And we're going to substitute this in to find our y value. So we have negative 1 squared, which is positive 1, which then we multiply by this negative, which gives us negative 1 plus 2 is positive 1. So here's our vertex, negative 1, 1. And I'm going to go ahead and add my axis of symmetry, so that when I'm plotting my points after the fact, I can see how to reflect about the axis of symmetry. To plot my additional points, setting up my table of values, my vertex is at x equals negative 1. So I'm going to plug in x equals 0 and x equals 1 again to get my 2 points on the right, and then I'll reflect those to get my 2 points on the left. When I plug in x equals 0, we get y equals 0. And reflecting that about the axis of symmetry, I get this point at negative 2, 0. When I plug in x equals negative 1, x equals positive 1, we get negative 1 squared minus 2 times 1, or negative 1 minus 2, which is negative 3. So 1, negative 3 is down here. Reflecting about my axis of symmetry gives me this point over there. And there's my parabola opening down. There are a couple ways that you can just check your work as you're going through. Make sure when you're plotting these points that the orientation ends up being correct. We know that it's going to open down from the very get-go because of this negative lead coefficient. If we start plotting points and we don't see that, then we need to check our math. Also, we know the shape is supposed to be a parabola, so it's always going to look like this or like this. If you're getting a shape that's different from that, maybe it looks like a cubic function, maybe it looks linear. Again, that's your indicator that you need to go back and check those ordered pairs to make sure that you're plotting or you're evaluating correctly and plotting those points correctly. (2x² plus 4). So again, we see a function that's missing one of those terms. It's missing our b term. So this function is the same as 2x² plus 0x plus 4. So now we can see the b, which is going to be necessary when we're finding our vertex. Since my lead coefficient is positive, we know it's going to open up. Now we'll find our vertex. Again, rewriting that formula every time, the negative b over 2a is going to help me remember that. Negative b is going to be 0 over 2 times 2. And 0 divided by 4 is just 0. And now to get the y value, when we plug in 0 for x up here, we're going to get 4. So our vertex is at 0, 4. And we know that this parabola is going to open up. We can go ahead and add our axis of symmetry and start making our table of values. Since the vertex is at x equals 0, I'm going to pick two positive values, x equals 1 and x equals 2, to find my 2 points on the right, and then reflect to find my 2 points on the left. You can pick -1 and -2, but generally speaking, it's easier to evaluate a function for a positive input. When we plug in x equals 1, we get 1 squared is 1 times 2 is 2. 2 plus 4 is 6. So 1, 6. If I've got a point at 1, 6 reflecting about the axis of symmetry, I also have a point at -1, 6. When we plug in x equals 2, we have 2 times 2 squared plus 4. 4 times 2 is 8, plus 4 is 12, which it looks like I'm actually going to run off my graph. It's somewhere way up here. And then if I reflect about my axis of symmetry, again, somewhere up there. And we can see that our parabola opens up like this. Now there's another form of our quadratic that we've actually seen in our previous lesson on transformations. The vertex form of a quadratic, f of x, equals a times x minus h squared plus k. Now when we look at this, this actually looks like our horizontal transformation, our stretch or our compression, our vertical shift. Something to pay attention to. Well, when we're in this form, our vertex is at the ordered pair h, k. Again, we're looking at the sign here. This is a negative, this is a minus sign. So if we end up with x plus a number, the h is going to be a positive value. Let's compare this quickly to our standard form, ax squared plus bx plus c. Obviously, we see that there's an h and a k in our vertex form, but we do have an a in our vertex form, just like we have an a in our standard form. Those two values are exactly the same. That value doesn't change regardless of the form that we're in. Obviously, the b and the c, there is a relationship between h and k, but they're not direct substitutions. But understanding that the a is the same is going to help us in the next couple examples. Now, when we're starting in our standard form, the ax squared plus bx plus c, and we want to convert to vertex form, we can do that by completing the square. There is one other technique that I'm going to show you guys to convert to vertex form that doesn't require completing the square, but I do encourage you guys to at least review the process of completing the square. If any of you plan on taking pre-calculus, you're not going to be able to avoid completing the square when you start talking about conic sections. So it is an important skill to have. Convert to vertex form, then graph the following function. F of x equals x squared minus 6x minus 1. I'm going to go through the steps for completing the square. If this is something that you feel like you maybe haven't seen before or you don't remember it, it is something I suggest that you maybe research a little bit more. You can look up some videos on YouTube, but I will show you another technique to complete the questions that we're going to see on our exams. So the first step for completing the square, we're going to take this minus 1 and just move it down. Just move it down. It's still there. We're just kind of putting it out of the way for a minute. And what we're trying to do is fill in a value here that completes the square of this quadratic. Now this value is going to be b over 2 squared. So I've got x squared minus 6x. This is my b. So in this value, it's going to be negative 6 over 2 squared. Don't forget, we still have the minus 1 there. Simplifying this, we've got x squared minus 6x. Negative 6 divided by 2 is negative 3. Negative 3 squared is positive 9. Minus 1. Now, if you look at this polynomial, if we were to combine like terms, we can see that we've changed it, haven't we? By adding this 9, it's no longer the same function that we had before. But what else could we do to this function so that it stays the same, but we also have to have that plus 9? If I add 9 to this side, I can also subtract 9, and that will keep it balanced. And now if you look here, if I were to combine like terms, we have our x squared minus 6x. Those will cancel out. Minus 1 is what we have at the beginning. And now we factor the quadratic at the front. So we've got f of x equals factors of 9 that sum to negative 6 are going to be negative 3 and negative 3. And we can write this as x minus 3 squared minus 10. Now, if you remember, the vertex form explicitly gives us the vertex. This tells me that my vertex is at positive 3, negative 10. We're going to change the sign of the value that's on the inside of the parentheses. We're going to keep the sign of the value that's on the outside of the parentheses. And if you were to kind of make the transition, kind of build the bridge back to transformations, if I start with a quadratic, my parent function quadratic, these transformations, this minus 3 in here tells me to move to the right 3, and this tells me to move down 10. So this entire graph is going to shift so that my vertex is at positive 3, negative 10. Which is what we have here. So to graph this, we had our vertex. It was at 3, negative 10. 3, negative 10 is down here. And if you remember, if you can look at your previous slide, the lead coefficient in the standard form was positive, and it was still positive in our vertex form. So we know this is going to open up. And now we just use the same technique. We're going to make a table of values to find two points on the left and the right of our vertex. So I'm going to plug in x equals 2 and x equals 1. So notice now I'm actually going to choose points that are on the left of my axis of symmetry, just because they seem like easier values to plug in. So we're going to plug in x equals 2, x equals 1. And let me rewrite the equations that we had. We had f of x equals x squared minus 6x minus 1, or in our vertex form, we had x minus 3 squared minus 10. Since these functions are exactly the same, they're just in different forms, it doesn't matter what we plug 2 and 1 into. We can use whichever one we like the best. Let's plug in 2 into the first one, into the standard form. 2 squared minus 6 times 2 minus 1. So we have 4 minus 12 minus 1. 4 minus 13, negative 9. And then to find f of 1, we'll use the vertex form. We've got 1 minus 3 squared minus 10. 1 minus 3 is negative 2, and negative 2 squared is going to be positive 4. Minus 10 is negative 6. So we're going to plot our 2 points. We've got 2, negative 9, and 1, negative 6. And both of those we're going to reflect about the axis of symmetry to get our points on the right-hand side. So that's how we can use completing the square to write our function in vertex form so that we can see the vertex without actually having to use the negative b over 2a. Convert to vertex form, then graph the function f of x equals 2x squared minus 4x plus 1. So here I'm going to show you a different technique for writing the function in vertex form. First, we're going to find the vertex using our negative b over 2a. Our vertex is going to be positive 4 over 2 times 2. And 4 divided by 4 is 1. And when I plug in 1, f of 1 equals 2 times 1 squared minus 4 times 1 plus 1. We have 2 minus 4 plus 1, negative 1. So that's our vertex. This is our h and our k. Our vertex form, f of x equals a times x minus h squared plus k. Now we're going to start substituting our values in. We know h and k, so we've got x minus 1 squared. K is minus 1. And now what about a? Remember what I mentioned about the vertex form and the standard form. That lead coefficient is still a. They're both a. It doesn't change. So since we had a is equal to 2 in my standard form, a is equal to 2 in my vertex form as well. So there's our function in vertex form. We can see that the vertex is at 1, negative 1, which we already knew because we used our vertex formula. And many of us think that this is a much easier way to write our quadratic function in vertex form. But again, just to remind you guys that eventually you're going to have to complete the square if you're taking pre-calc. So if you want to practice that skill now, I would encourage you to do it. So we're going to go ahead and graph. We had the function f of x equals 2 times x minus 1 squared plus 1. I'm just writing it for myself. Our vertex was at 1, negative 1. This should be a minus 1. So at 1, negative 1, our lead coefficient is positive. We know this graph is going to open up. And we'll make our table of values to find 2 points on the left and the right of our vertex. So I'm going to plug in x equals 0 and x equals negative 1. When I plug in x equals 0, we get 2 times 0 minus 1 squared minus 1. Negative 1 squared is positive 1, so we have 2 minus 1, or 1. Reflecting that about my axis of symmetry, I have a point over here as well at 2, 1. We'll find f of negative 1 next. 2 times negative 1 minus 1 squared minus 1. Negative 1 times minus 1 is negative 2, and negative 2 squared is 4. So we have 2 times 4 minus 1, or 8 minus 1 is 7. So we have a point at 1, negative 1, 7, which, man, twice I've had my graph's not perfect. But that's okay. So we've got that point up there. I graphed it in red so you could see it over that function. And then if I reflect this about the axis of symmetry, I'm going to have another point up here. And I can connect these points to graph my parabola. When you guys are preparing for your exam, graphing a parabola is pretty simple. Make sure you find your vertex and then plot 2 points on the left and the right of that vertex. Same every single time. I'm not really concerned about what points you plot on the left or the right. You don't have to find the x-intercepts or the y-intercepts, but if those work for you, you're always welcome to do so. There are questions that are going to require that you write your function in standard form as the vertex form. So no matter which technique you use, either completing the square or modeling it, finding your vertex, and then substituting the value of a, it doesn't matter to me. Just make sure that you're comfortable with one of those techniques. Next, we'll look at some applications of quadratics. The daily revenue, R, achieved by selling X boxes of chocolates is given by the following function. R of X equals 9.5X minus 0.04X squared. The daily cost of making X boxes of chocolates is given by C of X equals 1.25X plus 250. Now, we talked about the idea of cost and revenue. Remember, cost is what we spend to produce these chocolates, where revenue is the money that's coming in from selling these chocolates. Please make sure you remember the difference between revenue and profit because they're not the same thing. Profit is what we have left over after we've paid for all of our costs. How many boxes of chocolates must be sold to maximize revenue? We want to maximize the revenue. And then what is the maximum revenue? Let's first look at our revenue function. Our revenue function is a quadratic. I can rewrite this so that my quadratic term is first negative 0.04x squared plus 9.5x. And if I think about trying to find the maximum of a quadratic, where does that happen? Well, that happens at the vertex. This quadratic, R of X, if you can visualize it, since that lead coefficient is negative, it's going to open down, isn't it? Which means that the maximum revenue is going to occur at the vertex. So our vertex formula, again, negative b over 2a. We certainly don't want to complete the square for this problem just to find our vertex. Negative b is going to be negative 9.5 divided by 2 times negative 0.04. Now go ahead and take a minute, type this into your calculator. I'm going to find the answer here. When you simplify this, you should get 118.75. And now to find the y value of your vertex, go ahead and take this value of x and plug it into your function. So take a second now, maybe hit pause, type this into your calculator, make sure that you can evaluate it correctly. And when we evaluate our function at this 118.75, we get 564.06. Now, when we look at our question didn't ask us to find the vertex. Our question asked how many boxes must be sold to maximize revenue. Now, because it wanted us to maximize this thing, that's what indicated find vertex. But our vertex has two values, and we need to interpret what those two values represent. This first one is x. Well, what variable does x represent in our problem? X represents the boxes, the number of boxes. And our output Our output is R, so our output is revenue. So if I'm answering my questions, the first one asks how many boxes must be sold to maximize revenue. Well, I can't sell a fraction of a box, so I need to sell 119 boxes. And then what is the maximum revenue? That's going to be given by our Y value of the vertex. Our maximum revenue is going to be $564.06. You want to be very careful with the wording of the questions and make sure that you're answering the questions in the correct order. We're not just asking you to find the vertex in these problems, but also can you interpret the values of your vertex? If profit is equal to your revenue minus your cost, what's your profit function? We've seen an example just like this in one of our projects. Our profit function is going to be revenue 9.5x minus 0.04x squared minus my entire cost function. Make sure you use parentheses here. 1.25x plus 250. We'll distribute the minus sign, so we get 9.5x minus 0.04x squared minus 1.25x minus 250. We'll combine our like terms. Our profit function is equal to negative 0.04x squared. 9.5x minus 1.25x is 8.25x minus 250. And notice I arranged my terms so that it was in that standard form of our quadratic. And now that we have our profit function, how many boxes do we have to sell to maximize profit? Again, this key word here is maximize. That's indicating that we want to find the vertex. Formula for our vertex, negative b over 2a will find our x value. So negative b is going to be negative 8.25 over 2 times negative 0.04. Go ahead and hit pause. Evaluate this on your calculator. Our x value is 103.125. And now we're going to take this and plug it into our profit function to find the y value. When we plug in 103.125, we get 175.39. Again, if I look back at my question, it's not asking us to find the vertex. Because it wants us to maximize something, that's what's telling us to find the vertex. The first question is asking how many boxes must be sold to maximize profit. Well, we know that our X represents boxes. And now our Y, because we were using a different function, now our Y is representing the maximum profit. So our answer, we need to sell 104 boxes. And our maximum profit is going to be $175.39. Now I do want to talk about one thing here. Notice I rounded up to 104 boxes. Our decimal was 103.125. Well, we agree we can't sell a fraction of a box, but if we're using our general rounding rules, because it was a 0.125, we would actually round down to 103. But consider the real life application that we're talking about here. We're talking about selling boxes of chocolates and trying to maximize the profit. If I have to sell 103.125, that means I had to sell a portion of that 104th box in order to maximize profit. If I only sell 103, I haven't hit my maximum profit yet. So that's why we went ahead and rounded up to 104 boxes. The height of a football thrown is given by the function h of x equals negative 0.015 x squared plus 0.47x plus 6.1, where x represents the horizontal distance from the point of release. The first part is asking to find how far does the ball travel. It might help us to kind of get an idea of what this graph looks like. Now, we know enough about quadratic functions to get an idea or sketch this graph. We know that the y-intercept is going to be 6.1. We know that it's a quadratic, so it's going to look like a parabola because that x squared, and we know it's going to open down. So our graph is going to look something like this. Now, just knowing what this graph looks like can help us in identifying how we're going to answer these questions. The first one is, how far does the ball travel? Since x represents the horizontal distance from the point of release, that's going to indicate how far the ball traveled. So if I want to know how far the ball traveled, we need to find our x-intercept. Now we do have two x-intercepts, but again, thinking about real-life restrictions, if x represents a horizontal distance, a negative x isn't really meaningful because we can't have a negative horizontal distance. So this entire portion of our graph, we don't even consider. So we're finding one of our x-intercepts, and to find the x-intercept, we set our function equal to 0. So we have 0 equals negative 0.015 x squared plus 0.474x plus 6.1. Now to solve this, we can always try to factor, but that's not going to be fun because we have decimal coefficients. Our best bet is to use the quadratic formula. The quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. When we substitute our values in for a, b, and c, we get negative 0.474 plus or minus the square root 0.474 squared minus 4 times negative 0.015 times 6.1. All divided by 2 times negative 0.015. Go ahead and hit pause here and evaluate what x equals. You're going to have a positive and a negative, aren't you? Remember that we only care about the positive one because if we think about our real life restrictions, having a negative x value isn't relevant, isn't meaningful. So go ahead and pause this and evaluate this. And now that we're back, we get that x is equal to 41.42. What is the maximum height of the football? Well, our function is giving our height, so we're talking about, again, with the maximum, the vertex. Our vertex formula, negative b over 2a. We'll plug that in to find our y value. So substituting b and a, negative 0.474 divided by 2 times negative 0.015. Go ahead and pause now. Evaluate your x coordinate. We should get 15.8 for our x coordinate. And again, pause the video, plug in 15.8 to find your y value. 9.8446. If you're not pausing the video here and you're just taking my answers, that's fine for right now, but I do encourage you guys to make sure that you're comfortable using your calculator. When you guys get to the test, you're gonna have to be on your own as far as plugging this stuff in. If you're not comfortable with the functions of your calculator and how to type stuff in, you might end up with the wrong answer even though you understand the process. The question's asking for the maximum height, not the vertex. So which of these values represents the maximum height? The 15.8 is x. X, according to my problem, is a horizontal distance, so it's how far away it is. The y value is your height. So our max height is 9.8446. And since I didn't give any units in the problem, you don't need to worry about the units for your answers. But I'm pretty sure they're measured in feet. How far away is the ball when it reaches its maximum height? Again, if we think about our graph, here's our picture. It looks like this. We're still talking about the maximum height, so we're still talking about the vertex. But now it wants to know how far away was the ball. Well, if we have our vertex from the previous example was 15.8, 9.8446. Our x value is what talks about the horizontal distance. So that's how far away the ball is. How high was the ball when it was released? Again, think about that graph that we sketched that represents the function. We want to know how far or how high the ball was when it was released. Well, how far away is the ball when it was released? Well, it's 0 feet or 0 whatever units away. So we're looking for our y-intercept. And since we don't really need to do any arithmetic, our y-intercept is that constant when it's in standard form. It was 6.1 feet, meters, whatever. That's why I assume it's probably measured in feet. If a human's throwing that ball, probably not 6.1 meters above the ground. So again, just to recap this problem, we saw several different types of questions that indicate finding the different points along that graph. So talking about when it was released, how far away it is, we need to be aware of what these values represent in the context of the function. So make sure you understand what your variables are. That way, when it's talking about a certain measurement, you can identify whether they're looking for x values, y values, the vertex, and such. So my last example, if you remember a couple videos ago, you got to see a couple pictures of my dog Samantha. So this problem is in her honor. I want to enclose a rectangular pen along a river for my dog Samantha. I have exactly 400 yards of fencing, and I do not plan to fence the side along the river. That's because Sammy really likes to swim. She'd be pretty mad at me if I fenced her in and she couldn't swim in that river. What is the largest area that I can enclose? Again, that phrase largest area is making me think of maximum. When I think of maximum, what am I thinking about? Vertex. The same would go for minimum. You're going to see fewer problems dealing with minimizing something than you will with maximizing. But the problem is exactly the same. Find the vertex and interpret your x and y. Now, in order to find the vertex, I need a function which I don't have yet. So we're going to use the context of the problem to set up a function. So I'm going to draw a picture first. Here's my pen. Here's the river that I'm not fencing in. Here's Samantha. She's happy in her pen playing around. Now, I know that I've got 400 feet of fencing. Do I know how long this side of my pen is going to be? Nope. So I'm going to call it x. Since it's a rectangular pen, I know that this length is the same as this length, so that's also x. But how long is this side? I don't know that either, but I don't want to use y because I can't have too many variables. So let's think about our restriction of 400 feet, or 400 yards, excuse me. According to what I've drawn, oops, see if I can erase that. It's not bad. According to what I've drawn, I've only fenced 2x yards. I started with 400 and I've already used up 1x and another x, so I've already used up 2x. That represents what is left over. And since I only have one side left, that represents this third side. Now, if I think about area of a rectangle, because that's what I want to do, I want to maximize area. Area is length times width. Well, now my figure has a measurement for my length and my width. My length is 400 minus 2x, and my width is x. If I distribute this x, we get area is equal to 400x minus 2x squared, which is now a quadratic function that we can find the vertex that we thought we should do from the very beginning. I'm going to rewrite this so that it's in standard form. Negative 2x squared plus 400x. And now I'm going to start to find my vertex. Again, you can see that every time I use that formula, I'm writing it down. Every time I write it down, I write it, I think it, I say it. That's 3 times that I'm talking about that formula. I'm more likely to remember it when it comes time for that test if I've done this. So negative b over 2a, negative 400 divided by 2 times negative 2. Negative 400 divided by negative 4 is 100. And to find the y value, you'll go ahead and substitute the value of 100 into my area function. When we plug that in, we get 200,000. Looking back at your question, they want to find the largest area I can enclose, so the maximum area. So we need to interpret the values for our vertex. This x is corresponding to this x. That's the width of my pen. This is the output for my area. So my maximum area is 200,000 square yards, which makes Samantha a very happy girl. So we've seen several problems today. We talked about graphing a quadratic function. When we're graphing a quadratic function, we always start by finding our vertex. Now, if it's in standard form, we use our negative b over 2a to find our vertex. If it's already in vertex form, then we pick out our h and our k to plot that vertex. And then we always graph 2 points on the left and the right of your axis of symmetry. We also looked at some applications of quadratic functions. Optimization problems were the ones where we were finding the maximum or the minimum. And even in our last example, we saw where we had to come up with our quadratic function before being able to optimize it. We'll see you guys next time. Thanks.